Hello, chemistry family. Welcome back. I'm Michelle Saner, and today we are talking about balancing chemical reactions. So, by the end of this afternoon, I'm hoping that you're able to identify when a chemical reaction is balanced and that you can balance a chemical reaction on your own. So, let's take a little bit of information about the background. Last time we talked about conservation of mass and the various components of good chemical reactions, but I wanted to give you kind of a checklist. Your chemical equation, a good chemical equation, must represent all known facts. That is to say, we need to list all of the reactants on the left and all of the products on the right. We should have the exact molecular formula for each molecule. For example, the exact molecular formula of water is H2O. But we also need to know the correct ratio. How many of each molecule will it take to make that reaction go? And that's what the skill we're going to be working on today. Good chemical equations also include the phases of matter. So it tells you what are we talking about, a solid, a liquid, or a gas for each molecule. And it needs to contain all of the correct formulas, like H2O for the reactants and products. Finally, the law of conservation of mass must be satisfied. And to do that, we will balance our chemical equation and take that atomic inventory like we did last time. So how do we balance a chemical equation? To say that a chemical equation is balanced, we need to ensure that the law of conservation of mass is obeyed, that we start with the same number of one type of atom and we finish with the same number of that one type of atom. And just like Legos, we may be pulling them apart and putting them back together, but we're not going to lose any Legos. We're not going to lose any atoms in the process. Likewise, we're not going to gain and spontaneously appear any new Legos or atoms in the process. We say that the equation must be balanced, and we accomplish this by adding the appropriate coefficients. And again, these coefficients are the large numbers in front of a chemical formula that indicate how many of a certain type of molecule you'll need. A balanced chemical equation has the same number of each type of atom on each side, but we adjust the coefficients accordingly. So coefficients are numerically low numbers, 1, 2, 3, 4, that appear in front of a chemical formula in a chemical equation. Now, you can only add coefficients. You can't touch the subscripts. And what I mean are these little small numbers down here. You can't touch the subscripts. And I would like you to think about why that is. So stop for a moment and check in with yourself. See if you can answer this question. Pause the video. Why can you not change the subscripts in order to balance a chemical equation? See if you can come up with an answer on your own. All right, let's see how you did. Why can you not change the subscripts in order to balance a chemical equation? Because if you were to change the subscripts on a molecule, it would change the number of atoms in that molecule, and thus it would change the identity of that molecule. Here's an example. Let's say I was doing a balancing reaction and I needed to have two atoms of oxygen. Well, this compound is water. I cannot put a 2 there because I will have a completely different molecule. In this case, it's hydrogen peroxide. And that is a completely different molecule than water. There's an old joke that says two chemists walk into a bar, and the first says, I'll have an H2O, and the second says, I'll have an H2O2, and he dies. And the reason that joke is because an H2O2 is not water, it is actually hydrogen peroxide, which you should not drink. So we can't manipulate these subscripts when we're balancing the equation because we change the identity of the subscript. So I can't turn water into hydrogen peroxide simply by adding a 2 to its formula. I need to think of another way to balance the equation. And instead, I'll manipulate the coefficients in front of the chemical formula there in order to say I need more of these water molecules to make the equation balanced. So let's practice. So why would we do this? Well, conservation of mass is one of the single most important concepts in all of chemistry. And I just want to stop here and make sure that you realize if you can't balance an equation, you're going to have a very hard time completing the rest of the tasks in chemistry this year that require balanced chemical equations. So if it takes watching the video once, twice, 3 times, so be it. Let me show you a little example of what I mean by balancing equations. So I have a set of Legos from when my kids were little. The yellow represents hydrogen. So this is hydrogen gas. You could see in my chemical formula right here, one molecule of hydrogen gas is H2, meaning it has 2 atoms of hydrogen bonded together to form hydrogen gas. That's what that small 2 means. Now the coefficient 2 means that, hey, guess what? I have 2 atoms or 2 molecules of hydrogen gas here. And they are going to react with another molecule, O2. It's another gas, it's oxygen gas, the kind of oxygen that we breathe. It's made up of 2 different oxygen atoms bonded together. So what happens when I have a reaction that requires 2 hydrogen gases and 1 oxygen gas? Well, this reaction happens, the bonds break apart, they rearrange, and they reform. No new Legos are created or destroyed in this process, and I have 2 water molecules. Now, if I only had 1 hydrogen gas and 1 oxygen gas, and I tried to do this reaction, well, I would not be able to create 2 water. Let me show you how. Well, I can create 1 water molecule, but I have a leftover oxygen. So I have not created a true model. That's why I need to make sure that I start with 2 hydrogen gases and 1 oxygen gas, so that when I go to make these water, I have exactly the right amount. And here's a little kind of more like a bench shape to look a little bit more like water actually does. So conservation of mass. No atoms can be spontaneously created or destroyed, just like I can't spontaneously create Legos or make them magically disappear in this process. They're simply just taken apart and rearranged to form a new substance. But all of the pieces are still accounted for, even at the end when we have new products. So in chemical reaction, atoms, or matter in this case, are neither created nor destroyed, but rather simply rearranged by the breaking and forming of bonds. So here's a couple of tips for you to help balance your chemical equations in an accurate way. You want to start with the most complex molecules first. So the ones where you have lots of different types of atoms, the polyatomic molecules with many different kinds of atoms. Balance those first, and then the last ones are going to be the ones that only have one type of atom. If you only have one type of atom, it's really easy to decide how many there need to be. So do the complex ones first and the easiest ones later. The second tip I have for you is that the most correct balanced formula will have the lowest common multiple. For example, if I were to balance this reaction of 2 gases forming water, like I showed you in the model, 2 hydrogen gas form with 1 oxygen gas to create 2 water molecules is more correct than 4 hydrogen gas reacting with 2 oxygen gas to form 4 water molecules. So if you have a sentence where you have a situation where all of your coefficients 4, 2, and 4 are divisible by a common multiple, in this case, they're all divisible by 2, then you simply reduce. And your reduced chemical formula, your lowest common multiple formula, is the most correct one. So you may be working back and forth between the reactant side and the product side, carefully keeping track using the atomic inventory we did last time, carefully keeping track of the changes that you make. And at the very end, count up your atoms on each side one final time to ensure that you have the same amount of atoms of each type on both sides, and double check your final answer. Okay, so let's practice a few of these. All right. In my first example, I see that I have a nitrogen and a hydrogen. They are going to react and form a new compound. So I'm going to start with how many I have. I have 2 nitrogens, as indicated by that subscript there, reacting with 2 hydrogens, as indicated by the subscript there. Over here on the product side, I have 1 nitrogen which is implied by the lack of a subscript. And some kids will get confused because they'll see nothing there and they'll be like, oh, there's 0 nitrogens. But remember, there can't be 0 nitrogens or we never would have even written the N to begin with. So the presence of a letter by itself just means that, hey, you've only got one of that type of atom. And then over here, I've got a subscript of 3 on the hydrogen, meaning there are 3. Now, I'm ready to start balancing. I can put new numbers in front to say, hey, listen, I know nitrogen and hydrogen are going to react to form this molecule here, but how much am I going to need of each of these for this to work? Like with our old example of the bicycle, how many wheels will I need to make a bicycle? You're not changing the structure of the wheel, you're just adding more of them or taking away some of them. So I'm going to go ahead and start with the most complex molecule, which in this case is the only one that has 2 different types, NH3. Now, I have 2 on one side and 3 on the other. I can never turn 2 into 3. There's no number except, fractions that I can use to get 2 into number 3. But I can maybe double everything here, which takes my hydrogens up to 6 hydrogens. 2 times 3 is 6. And it makes my nitrogens have 2 nitrogens. So every time I make a change here, go ahead and edit your atomic inventory with the new updated information, and that'll help you keep track as you go. Okay, back to the reactant side. 2 and 2 are good. I'm balanced in terms of nitrogen. So I could either leave this blank or I could put a 1 if you were uncomfortable with blank spaces. But a 1 is always implied as a coefficient if there's nothing there. And then what number could I put here for H2 in order to end up with 6 hydrogens? Well, if I put a number 3 here, 3 times the fact that there's 2 of them, 3 H2s gives me a total of, of 6 hydrogens. And now my 6 on this side, my 6 on this side are balanced, and I can check off that this is a complete and balanced reaction. Okay, let's do one more together and then we can try some on our own. Here, remember my tip, always start with a more complex molecule. So I am going to start with the molecule that is a product. I see that there are 4 phosphorus atoms and 10 oxygen atoms there. Moving over to this side, I see that I have 4 phosphorus atoms. So that looks pretty good. It looks like phosphorus is balanced. Put a 1 there. And 2 oxygen atoms. I need to get the 2 up to 10, and I can only change the values in front of the oxygen gas. So if I put the coefficient of 5 here, 5 times 2 is 10. So 4 is balanced, 4 phosphorus, 10 oxygen atoms on both sides. And you can write in a 1 coefficient there if you don't like the implication of there being nothing there. All right, so I would like you to pause the video and try the following problems on your own. As always, write out your atomic inventory before and after for the products and the reactants. And from there, try to adjust the coefficients in these blank spots so that the number of atoms is the same on the product side as it is on the reactant side. Let's see how you do. Okay, so I'll talk you through it and then you guys can check your work and see how well you did. I'll just start with this more complex polyatomic ion here, or a polyatomic species. I've got 2 aluminums and 1 atom of oxygen on the reactant side. Over here on the product side, I have an implied 1 aluminum and 2 oxygens. Okay, so working back and forth, I'm going to go ahead and stay with this more complicated one. I have 2 aluminums and 1 aluminum here, but before I do anything, I want to take care maybe of this oxygen. I need to get this up to 2. So I'll put a 2 here. And in doing so, I double everything. I double the number of aluminums from 2 to 4, and I double the number of oxygens from 1 to 2. So now my oxygens are balanced, 2 and 2 on each side. So coming on back to the simplest after the fact, I could put a 1 there since I'm done. Aluminum, how do I get 4 aluminums from 1? Well, I'll just put a 4 there. And now I'm done. I have a balanced reaction. Check and check. doing the same thing, always start with your more polyatomic species, or the one that has a lot of different type of atoms in it. So I have 1 nitrogen and 3 hydrogen. Over here, I've got 2 hydrogens and 2 nitrogen. And I can already see in the hydrogens that we're going to have a problem. I can't put anything here to get to 3. Remember, the coefficients need to be whole numbers, so I couldn't just put 1.5 there. I could, however, bring this up to 3, which turns my H's from 2 to 6. And then working on the other side, I have 3 hydrogens, but if I put a coefficient of 2, that doubles everything. It doubles the number of nitrogens, and it doubles the number of hydrogens, 3. So 2 times 3 is 6. So look at that, my hydrogens are balanced. I check those off, those are done. To balance my nitrogens, I have 2 on the product side, 2 on the product side and 2 on the reactant side, so I am balanced. And that is how you balance chemical reactions. When we meet again in class, we're actually going to do quite a bit more practice on these, because this is a really important skill. Everything that we do beyond this unit will rely on having a balanced chemical reaction. And you can't always assume that I've balanced them for you. So take your atomic inventories, count up your number of atoms on each side, and if they match, you have a balanced chemical reaction. If not, you are free to adjust the coefficients, that is to say the larger numbers in front of the molecule, in order to achieve conservation of mass. I hope you're doing well and that you're having a great day. And I'll see you next time. Bye.